today at the very beginning, we're going to be doing a few new things. It's important that you write down these identities so that you have them in your notes for reference when you're working on problems for homework. And they're going to be our fundamental trig identities. So we're going to start with what we call reciprocal identities. And we have 6 reciprocal identities, one for each trig function: sine, cosine, tangent, cosecant, secant, cotangent. And reciprocal identities are really pretty easy for us. You're going to be responsible for knowing the identities in Chapter 5. And these, I don't think, require a whole lot of study or memorization or anything like that. So I'm actually going to focus on the ones over here on the right side because we're probably most familiar with these already because of our calculator work in Chapter 4. So cosecant x is equal to what in terms of its reciprocal? What would you type into the calculator to do a cosecant? 1 over sine, right? So it's the reciprocal of sine. So we can say that cosecant x is 1 over sine x. And then secant x is 1 over cosine x. And cotangent x is 1 over tangent x. So we're relating the reciprocals to each other. Note that cosecant is not equal to sine, it's equal to the reciprocal of sine. And so then think about how that would translate if we're doing the basic trig functions. Sine of x is equal to 1 over cosecant x. And cosine is equal to 1 over secant, and tangent is equal to 1 over cotangent. Now, I would guess a lot of us prefer, if possible, to work in terms of sine, cosine, tangent as compared to those reciprocal functions. So we're probably going to use more of the second column ones, but there will be times when we're working on a problem, and if your problem finishes with something like 1 divided by cotangent, then you would really want to simplify that one step further and just call it tangent, because that's easier than a reciprocal. Okay, so you might use all 6 of those reciprocal functions. Now, we also have some identities that are called quotient identities. And instead of having a quotient identity for all 6 trig functions, we only have a quotient identity for 2 trig functions, tangent and cotangent. Now, this really comes from Chapter 4 and your unit circle. So this is going to come in handy on the next 2 slides. Remember, on the unit circle, we would have theta right around the origin there. And we said on the unit circle that the y-coordinate was equal to the sine value of that angle, the x-coordinate was equal to the cosine value of that angle, and the tangent was equal to what? Tangent was equal to y over x. Very good. Okay, so if we said that x is really cosine and y is really sine, then by substitution we could say that tangent is actually sine over cosine. So that's our quotient identity. Sine of theta divided by cosine. Oops, these are in x's, not thetas. Sine of x divided by cosine x. So that's a quotient identity. And cotangent then would be cosine x over sine x. So those you'll need to know in the future. I might spend a little bit of time studying those. Not real hard, and we'll use them quite a bit, so I think you'll get the hang of that one, and it'll kind of stick in your mind. The next set of identities are called Pythagorean identities. Okay? Pythagorean identities makes me think of Pythagorean theorem. So again, I'm going to draw a quick image of my circle from Chapter 4 and that triangle there. I'm going to label the x cosine and the y was sine and the radius was 1. And in that circle, don't you agree, if we did Pythagorean theorem for that right triangle, sine squared theta plus cosine squared theta would equal 1? So that's where that comes from. Sine squared x plus cosine squared x equals 1. Now there are some different versions of Pythagorean identities. So these are a little bit harder to remember. Probably going to need to spend some time looking these over and studying them. If you're a note cards kind of person, this is a great chapter for some note cards so you know your identities. 1 plus tangent squared x is equal to secant squared x. And 1 plus cotangent squared x is equal to cosecant squared x. Now we're going to be using these identities in problems to do what you did in the doublets activity, which is like replace a letter. So we're going to be replacing a trig function with something else. We're going to be doing substitution. So with the trig identity, or sorry, the Pythagorean identities, note that we have these Pythagorean identities written in these ways to start with, but you can always adjust them in different ways. So like sine squared x plus cosine squared x equals 1. You could also say that sine squared x was equal to 1 minus cosine squared x. You just move it around, manipulate the equation. In the same scenario, we could say cosine squared x is equal to 1 minus sine squared x. So you have some flexibility with the Pythagorean identities where you can move things around, like by adding and subtracting from both sides. And this will make more sense when we do some examples, but I always kind of keep an eye out for things that are squared, especially if I have ones with them, and I think, oh, there's a 1 plus something squared. Is that a Pythagorean identity? Could I just substitute something real quick? Like if I saw 1 minus sine squared, could I change that into cosine squared? So you might think about that as you're working through problems. And one more set of identities are your even-odd identities. I'll let you write those down and then I'll talk about them. Put a line through the middle there because the top two are really similar. The sine and tangent families, and the cosine's a little bit different. The even-odd identities come from, if you remember all the way back to chapter 1, even-odd functions. So even functions are functions that are symmetric to the y-axis, and odd functions are functions that are symmetric to the origin. I'm going to start with the even functions, which would be the ones down here like cosine and secant. So do you remember when we graphed cosine, it started up at the y-axis at 0, 1, and then it came down and went like this. So if we kind of copy and paste that on the other side, it looks something like this. And so this is symmetric to the y-axis. It reflects onto itself. Okay. And so this is an example where f of negative x is equal to f of x. Meaning, if I am doing like this point right here, which would be the cosine of like pi over 6 is 1 no, cosine of pi over 3 is 1/2. Then if I do the cosine of negative pi over 3, that's the same same value, 1/2 on the other side. So the y value is the same if you flip the x. And then these are really examples, which is what you see here. Change the x, but it's the same thing, the cosine of x. Okay, so it's doing this piece right here. These up here are really your odd identities. So like sine was the one that went mountain high, valley low. So if you imagine extending that on the other side, if you were to rotate that around the origin, it'll map onto itself, so it has odd symmetry. And same with tangent. Looks something like this. Rotate it and it'll map onto itself. And these are examples where when you put in the opposite value of x, you get the opposite value of y. Okay? So like if you're doing the sine of pi halves, you would get positive 1. But if you change it and you do the sine of negative pi halves, then you get negative 1. So those are odd functions. And you see that. If you put in a negative x, then the sign becomes negative. So just so you kind of know why those identities are what they are. Now before we get into any examples, there's one other thing real quick we want to talk about, and that is factoring trig expressions. So factoring trig expressions is a thing that we're allowed to do. And the best thing I could say is when factoring trig expressions, think about it just like factoring polynomials. It's really the same thing. The difference is that your variable, like maybe it was just x with a polynomial, is now going to be replaced with a sine of x or a cosine of x or some other trig function. So I'm just going to show you a quick example where I'm going to give you two factors, and then we'll multiply them and see what that looks like in trig form. So let's say that our factors, like a factor used to look like x minus 3. Let's say we replace x with sine of x. So we'll say the sine of x minus 3 times the sine of x minus 1. So those would be like what the factored form will look like. Instead of x minus 3 and x minus 1, they're going to have sine, cosine, tangent, whatever. If you were to multiply this out or FOIL this out, sine times sine would be sine squared. Okay, so you'll get a sine squared. And to write a trig function squared, you put it right after like the sine, cosine, or tangent. You're not squaring the x, you're squaring the trig function. Sine x times sine x. And then you would do your outside terms, which would be minus 1 sine x, and your inside term minus 3 sine x, so that will be minus 4 sine x. And then you'll do your last term, negative 3 times negative 1, which is a plus 3. So you're going to be on the lookout for things that look like this piece over here on the right, sine squared x minus 4 sine x plus 3. And when you see that, you're like, oh, hey, a trinomial. I can factor that. It's going to be sine x minus 3 sine x minus 1. So you can think about it in your head as these are really just like the old polynomials, but they've got the trig functions in them. So here's an example that we can factor. 2 cosecant squared theta minus 7 cosecant theta plus 3. So I see a cosecant squared and a cosecant. I see that there are 3 terms, so I'm thinking about a trinomial. And I want to factor that. To get that first term of 2 cosecant squared theta, what would I have multiplied together? What's that, Hugh? 2 and 1, and what will get me cosecant squared? Cosecant times cosecant. So it must start out first terms 2 cosecant theta and cosecant theta. And you're thinking in your head, if I were to FOIL that out, first terms times each other, 2 cosecant theta times cosecant theta will be 2 cosecant squared theta. Okay. Then I go to my last term. What multiplies to make 3? Yeah, 3 and 1, not hard, right? So you just have to decide where you're going to put the 3, where you're going to put the 1, so you get the correct middle term of -7. -3 goes in the second one. Okay. So -3, because then when you multiply by the first term, that's -6 cosecant. And then we'll have a -1, so that we get the -1, which is -7. And then if you were to do your last terms, -1 times -3 is +3. Now, so you'll be on the lookout for trinomials, and those are a little bit easier to spot. There are some, and this is one that I think would be really hard for newbies to factor in, to see how to factor this, just because it looks so different than what we're used to. So it looks like sine squared theta minus cosine squared theta. And, you know, if I were just looking at this at the beginning, I'd think, well, gosh, how do I factor that if they're not even the same kind of trig function? So this is one, just kind of give you an idea and some experience with. This is kind of like x squared minus y squared. You know, just if I was thinking about it like variables. And then some people might say, well, I'm still not sure how to factor x squared minus y squared. Think about it like this. These are both perfect squares. So if I gave you something like x squared minus 9, you would tell me that factors as x plus 3, x minus 3. So x squared minus y squared would be x plus y, x minus y. And sine squared theta minus cosine squared theta would be sine theta what would I put after that? Plus cosine theta. And my other factor would be sine theta minus cosine theta. So you're just kind of following a pattern there. Now, that's less common for you to come in contact with, but there are some times where you can kind of utilize that difference of perfect squares factoring. So if you see that, you could use that. Okay, next up are some tips for simplifying with trig identities. This is like, what are we really trying to do in this section? So then we're going to get into some examples so you can see what your homework's going to look like. Here are some things you can try. These are my 4 hints to you. If possible, try write everything in one trig function. If you can get them all in terms of sign, then maybe they'll combine together or cancel out or do something and make it simpler. If you can't get it in one trig function, then try getting it in terms of only sines and cosines. Now, sines and cosines are related in the Pythagorean identity. Sine squared plus cosine squared equals 1. They have the quotient identity. Sine over cosine is equal to tangent. So, if possible, getting them in only sines and cosines can be helpful. You might be on the lookout for factoring. I'm going to put a little reminder there. Don't forget that in addition to factoring, you also have Pythagorean identities that have squareds in them. So just because you have sine squared and some other terms doesn't mean that you have to factor it. It might also be better to just substitute with Pythagorean identity. And then my last tip is combine fractions. Now, I guess there's two ways to combine your fractions. You could be adding or subtracting them. In that case, you'll need common denominators. Or you could be multiplying them. So in that case, you can cross cancel or reduce. If you're ever kind of like walking yourself into a wall and you're like, wait, I don't know how to add these fractions, make it simpler. Just think about how do you add fractions in regular math when they're not trig functions and they're just numbers or variables. Okay? The same rules apply. So we're going to work as a group to simplify some expressions. I put these in your notes just for examples. But remember, when you're doing your homework, we can do them differently. Nathan can work it out, same starting point, same ending point, and have a whole different middle than McKenna does. Totally fine. Both of them would be following the identities or the rules, and they should have correct work in the middle. Here's our first example. Cosine squared x times cosecant x minus cosecant x. All right. All my directions are going to say are something like simplify the trig expression. The heck does that mean, right? Like, write it so it has less trig functions in it, see where it goes. It's just like these problems you're doing on the doublets worksheet. Do one step at a time, have a reason for doing every step, and see where it could take you. If it's taking you into something really long and complex, maybe backtrack or restart, right? Don't let yourself get so confuddled with it that you give up all hope. Okay? So, any ideas on where we could start changing things? Lauren?
Can you divide this by cosecant x?
No, because there's not an equal sign. And I will also encourage you not to divide by cosecant x in the future, only because like if we're solving an equation, which we will be doing, if you divide by cosecant x, there could be a solution, cosecant x equals 0, and then you're going to be missing that solution. So rather than dividing things out, what can you do that's like dividing but not canceling it away? You could factor it out. So we could factor out cosecant x. Does anybody else have a different idea besides dividing cosecant x? I thought I saw another hand out there. No other ideas? Okay, so we could try factoring cosecant x out of both terms. I think that's allowable. If you factor cosecant x out of the first term, what's left over? Cosine squared. And when you factor cosecant x out of the back term, what's left over? Minus 1. So don't forget, it's not just going to like disappear. There's a placeholder there, minus 1. So that if I redistribute the cosecant x, it's the original problem, right? And my reason for that would be factoring. Okay. Zach.
You could factor the cosine x squared x minus 1.
Yeah, you could factor cosine squared x minus 1. That's a difference of perfect squares, right? So if I factor cosine squared x minus 1, and I do cosine x plus 1 and cosine x minus 1, do you see something, Zach, since that was your idea, that you want to do next?
Couldn't you use a Pythagorean?
What? Okay, so look at your Pythagorean identities. What do you notice about all the trig functions in the Pythagorean identity? They all have what on them? The squared, right? So this is one where like I factored this, and now I have 3 things, and like in order for me to really do anything, I'm going to have to re-multiply stuff. So this is one where, like, I'm not sure this was my best option. Now, you can work with this, and you'll get to the right answer. It's going to be more work. So I'm going to say, I'm going to backtrack. It was a great idea. It works. It was allowable. But instead of factoring, maybe I should have just done Pythagorean identity. So I'm going to put my reason down here as Pythagorean identity. Cosine squared x minus 1 is equal to what in the Pythagorean identity? Might have to do a little bit of work for that. Sine squared x plus cosine squared x equals what? Negative sine squared x. Subtract 1. So you have cosine squared x minus 1, and then you have to subtract sine squared. So you can replace cosine squared x minus 1 with negative sine squared x. Does that make sense to everybody? Cosecant x. I'm going to put it in parentheses, negative sine squared x, just so it doesn't look like minus, right? It's being times by a negative sine squared. Okay, ooh, I like that. I'm down to 2. What next? Zach has an idea. Anyone else? Which set of identities do you think we might be utilizing? Talk to your group members real quick. Tatum, what did your group say? No idea. Oh man, Abigail, what did your group say? Maybe use a reciprocal identity. Hey, how are cosecant and sine related? They're reciprocals. So let's rewrite cosecant as 1 over sine x times negative sine squared x. That's my reciprocal identity. Now I'm thinking I'm probably not going to reuse my Pythagorean identity because that would like backtrack me, right? So I'm really looking at that moment at cosecant. What can I do with cosecant? Rewrite it as a sine. And then what happens when you multiply 1 over sine times the negative sine squared? You're just going to get negative sine, right? The sine in the denominator is going to cancel out one of the signs in the numerator. It's going to reduce, cross cancel. So then you have negative sine x. So I'm going to say cross cancel, reduce, multiply, something like that. Questions? It's not the only way to do that problem. What Zach did originally with the factoring, we could have continued with that and then some distribution got somewhere. It just would have been longer steps. So there's sometimes that way to work smarter, not harder. Maggie?
How would you cancel out the square if you don't have a square root or something?
It's like, I'm doing a little bit less work than I need to, but I'm really multiplying. So if I multiply across on top, that's negative sine squared x. And then if I multiply across on bottom, that's a sine x. And remember, a sine squared is like a sine times a sine, right? And so then one of the signs is going to cancel. So from now on, if you have like cosine squared x over cosine, you can cancel out the square on the top, and then it becomes just a cosine. Any other questions out there? Let's try another one. Cosecant x times secant x minus cotangent x. little bit different than the last one. Lauren's idea doesn't really work here, right? Which was to factor, or try to like divide by something, but we only divide by something, we won't factor it out. What other possible things in my tips might be helpful here? You? Not really any fractions to combine. Can you write them all in one trig function? No. Can you all write them all in terms of sine and cosine? Yeah, let's do that. So cosecant x would be 1 over sine x. Secant x is 1 over cosine x. And then cotangent, we could write 1 over tangent x, but that's still 3 different functions. Use your quotient identity. It's cosine x over sine x. So I'm okay on this one. Like, I'm going to say this is my reciprocal and my quotient identities. If you feel like that's too much for you and you'd have to do that in 2 separate steps, you could. Okay, cool. Now they're all in terms of one trig function. What do you think you might want to do with them now? Some people might have like, oh, could I cancel something? Right? Sometimes that pops into our mind. Be careful here if you are thinking about canceling cosines. Can't cancel cosines in this one because they're being subtracted, not multiplied, so the cross canceling doesn't work. But since I do have 2 things that are being subtracted, I could combine those fractions if I had common denominators. So over here, this is really 1 over sine x cosine x. In order for me to be able to subtract, this fraction needs a cosine x in the denominator. So I'm going to multiply by cosine x. So that's going to give me cosine squared x over sine x cosine x. And so maybe I'll just say common denominators for my work there. And then I could subtract them, right? 1 minus cosine squared in the numerator. And sine x cosine x in the denominator. So I'm going to say subtract. So sometimes your reasons are really just like math that you're normally doing. Okay. What sort of pops into your mind at this point? Very good. If you look back at your Pythagorean identity, if you subtract cosine squared x from both sides, then 1 minus cosine squared x is equal to sine squared x. So we could take that whole numerator and write sine squared x. Thank you, Paige. So that's my Pythagorean identity. Now, you might need to do this little bit of work over there where you like add and subtract. You'll get used to using the Pythagoreans lots of times, so then maybe you'll know, okay? But this one is positive sine squared. The other one was cosine squared minus 1, so it was opposite. Okay, so it was negative sine squared x. And then what happens? Cancel. Thank you, Tatum. Cancel sign on the top and the bottom. And I get sine x over cosine x. I'm just going to say I'm reducing right there. And then sine x over cosine x, tangent. So most of the time, when you're doing these problems, it's going to simplify to like one trig function. Okay. Now there are some problems where like maybe there's a couple of trig functions in the final answer, but it should come out to something like that seems, oh, that's much better than what it was before. Okay, so be on the lookout for that. If you start heading in a direction, like if you were to factor this, and then everything is getting bigger and bigger and more complicated to keep track of, you probably want to backtrack and think about, was there another route I could have taken? Was there a fork in the road and I could have went a different way? Maybe I'll try that way instead. Just like with the doublets activity. Maybe instead of changing it to one word, you change it to a different word. Okay, so don't be scared to retry. Any questions on that one? Okay, there's one other type of example that's going to be on your homework that I want to talk about, and that's the trig substitutions. This is what the directions are going to say. Write the algebraic expression as a trig function of theta, where 0 is less than theta is less than pi halves. And then this is what the problems are going to look like. They're going to give you an algebraic expression, the square root of 25 minus x squared. And then they're going to give you that variable in some trig form. So x is equal to 5 sine theta, which x is equal to 5 sine theta can come back to us later on in chapter 10 in terms of polar coordinates. So there are some connections to our later chapters here. Key word on these types of problems is substitution. So when you substitute, you're plugging something in, right? This is your algebraic expression. Plug in for x. So I would start by writing the square root of 25 minus, and then instead of x squared, I would have 5 times sine theta squared. If you're squaring all of 5 sine theta, then you have to square the sine and the 5, right? Okay, so that's really 25 minus 25 sine squared theta. Beware the pitfalls here. The square root of 25 minus x squared is not equal to the square root of 5 minus x. That's not a property of radicals. When we get down here, the square root of 25 minus 25 sine squared theta is not equal to 5 minus 5 sine theta. You can't square root when there's plus or minus. What do you notice about both of these terms? They both have 25. Factor out 25. So you're left with 1 minus sine squared theta. And then 1 minus sine squared theta sounds kind of like Pythagorean identity. 1 minus sine squared theta is equal to cosine squared theta. And now I don't have plus or minus. Can I square root both of those if they're being multiplied? Sure thing. So this is going to simplify to be 5 cosine theta. If you feel like you might fall into a trap, make a little note. This is not equal to 5 minus 5 sine theta. The square root of a plus b does not equal the square root of a plus the square root of b. That is not a rule. You made that up if you use it. Okay? That one I don't necessarily require reasons for because you're just doing the substitution and it's going to work out very similarly each time. Okay? You'll have a homework assignment over the weekend. Okay. Best thing I can say is give it a go. If you refuse to start, if you're paralyzed by fear, you're not going to get anywhere, and it's going to be a hard chapter from the get-go. So write down a problem, look at the top 4 tips that I gave you, try something. If in 3 steps you're not seeing a light at the end of the tunnel, maybe backtrack and see if you could try something different. If one problem gives you a heck of a time, circle it, move on to the next. Okay, you'll get some of them you might get stuck. It's just like the doublets.